So welcome. Today we're going to be talking about policy gradient methods. This is your first time to San Diego Machine Learning, or if it's been a little while, all our events are on Meetup. Check us out. We've got our GitHub repository where you can see links to slides, recordings for the previous sessions once we get them up. So today's topic, policy gradients, really kind of kicked my butt. There's a there was math in some of the early stuff we did, but there's a very different math in this, and so I think I've managed to distill it and get it right. We're not showing all the math and all the proofs today, but hopefully this will give the intuition for people who want to go back and read the full chapter in Sutton Barto, or who are reading papers in reinforcement learning. A lot of the papers these days use policy gradient methods. So hopefully that will help, but let's just first do our usual. So in terms of how to participate, this is informal. Feel free to just, actually not just feel free, but I request that you actually stop me at any point. If you have a question, you can just unmute, ask the question. If your microphone's not working, put it in chat. Want this to be interactive. And what we're going to do is we're going to do a quick recap of key parts of what we've been talking about up till now. Up till now, it's really all been about using value functions to do reinforcement learning. And today, with policy gradients, where the key aspect does not involve value functions, but then you'll see we're going to merge them back. In actor-critic methods, we're going to actually use both the policy gradient techniques and the old value function techniques. So that's the plan for today. So here's our really quick recap. So we've formulated reinforcement learning as a problem where you've got an agent in an unknown environment, and all you're getting in each time step is a scalar reward signal. It's a positive or negative floating point number. And what you're trying to do is you're trying to maximize the total reward. So not the short-term return from one step, but the long-term rewards over time. And how we do this is we model it as a Markov decision process. So the key thing in a Markov decision process is that when you're in a certain state, when I'm in state 13, it doesn't matter anything that happened beforehand, how I got there. The only thing you need to know is everything you need to know is bundled in the fact that you're in state 13, not 12, not 14, not 7. In real life, the problems are not necessarily perfectly Markovian, and so this is sometimes an approximation of your real environment. And so there's various things we talked about. You can model it as a graph, and ultimately you can try and say, I'm going to estimate the value for a particular state, or I'm going to estimate the value for a particular state action pair. And so we've got different terminology that we've been using. We use G, which is the sum of all of the future rewards. They could be discounted. We have a discount rate gamma. The value for a particular state is V. When it's estimated, usually it's capital V. When it's the true unknown behind the scenes, it's lowercase. And then for a state action combo, I'm in state 17 and I do action 2, then that function is Q. And we use the Greek letter pi to represent a policy. So we're going to see a lot of pi and a little bit of Q and V too today. So not going to talk about it so much, but underlying this, we've always said that the value, so the sum of all the rewards over time that you're going to get from a particular state, involves the probability that you take an action. That's your choice, that's your policy. And then the probability that you wind up in get a particular reward and wind up in a new state. That's the environment. You have no control over it. Okay, times the reward plus the future value from one step ahead of now on forward. And the key thing here is that you are multiplying this probability of what reward and state you're going to wind up in times these rewards. And you're also multiplying this product by the probability that you take those particular actions. I'm emphasizing this because this is going to come up in our policy grading discussion. So this is, this is a sum, but if you distributed this out, basically you would just get a sum of a lot of terms that are product of three things, okay? The probability of action one times the probability you wind up in a particular state and the rewards, and then probability of action one times any other state that you might wind up in the rewards, and then you got action two, blah, blah, blah. So it's just gonna be a sum of a lot of three-term products. On the value side, we then went through and we used the Bellman equation, we used the optimality equations to ultimately come up with update rules to say if I have an approximate value estimate for a particular state or state action pair, then if I get some data coming in from experience with the environment, can I then use that to incrementally tweak my estimates in the right direction? And so that gives us this idea of generalized policy iteration where we have some value estimate and we use that to tweak our policy, our choices of what actions we do slightly in the right direction. And with a slightly tweaked set of actions, we then may get a slightly tweaked update to our value. And then we can repeat, oftentimes millions, billions of times. And you can kind of prove that for like a finite Markov decision process, this will actually converge in the limit to the global optimum. So you will get accurate values, and you can also then, if you know the value of every state and every action, then obviously you can pick the best policy because you just take the max of everything. So that's generalized policy iteration. That's all our action value learning algorithms. So two algorithms that we talked about, and we're going to reference them tangentially. So one was Monte Carlo method. So you pick a random starting state, and what you do is you just repeat it many, many times. Here, you calculate G, you calculate the return from that starting point. And if you do this, 1,000 times, a million times, and you average it, you should get a very good estimate of what is the long-term return from a given state under your current policy. Okay, so that's one way that you can estimate what is the value of a particular state in action. We then kept going and we got into temporal difference learning, and we saw that you don't have to actually wait until you complete an episode, potentially 5, 10, 100, thousands of steps later. You can actually start doing updating right away. And so the TD0 algorithm says if we know the reward we got from taking one step and our estimate for the value of the successor state, well, the sum of those two basically is supposed to be the total return. So if we sum those and we subtract what our current estimate is for our current state, then if this is non-zero, that means that this new data we got, this actual reward we got, is helping us improve our current estimate. But we don't lump that all in. What we're doing is we're going to repeat this many times, and so we're going to multiply it by small learning rate alpha. So that's the TD algorithm, and again, we'll reference those somewhat tangentially as we talk about policy gradients. All right, so that's the big setup. Let me just pause here if there's anybody new or if there's anything I said wrong or went too fast. Any comments or questions before we now get into how policy gradient methods differ from the action, the value-based learning that we've talked about in the last like 5-6 sessions?
I'm curious about relationship between alpha and gamma, because it looks for me that the lower is gamma, then alpha could be chosen greater, right? Is there anything in the book about it?
No, I mean, basically you want these updates to be small because you are sampling, right? So you could just by luck have a very big reward or a very small reward or a negative reward or a positive reward. So you do want alpha to be relatively small. This can be done discounted or undiscounted. So gamma could be 1 and this works. Now, it turns out that if your gamma is very small, then that means that you are not valuing the future very highly. You're really saying that my short-term reward is mostly all I care about. That actually, in practice, simplifies things because now it's a short-term optimization problem instead of a long-term optimization problem, right? So
Mhm.
imagine the case where gamma is teeny tiny 0.01. Effectively, you don't even care what happens 2 steps from now. It's 99% just going to be whatever the reward is from your 1 step. So then you hardly even need reinforcement learning. You can just simply say, well, if I check out, if I have 4 actions, up, down, left, right, if I just check out those 4 actions a dozen times, I probably have a pretty decent estimate as to, which is best. Does that make sense?
Yeah.
Thanks. Any other questions? Okay, so that's all the value-based learning, and we've talked about, how we can do planning and different things on top of that. So we're now going to switch gears and we're going to say, we're not going to use any value functions at all. We're not going to use an intermediary. What we're going to do is we're going to say, what if I just built you a function, okay? And you said, hey, I'm an agent. I'm currently in state 17. What do you want me to do? And the function just simply outputs, 10% go up, 25% go down, 30% go left, 40% go right. Okay? So that's not using values anywhere as an intermediary, and we're not doing any of that kind of, uh, policy iteration where we're tweaking our values and we're basing our policy choices on the values. We're just directly saying right now we're not saying how we would build that function, but we're simply saying I'm building a function that just simply outputs probabilities. Okay, so this function is going to have some sort of parameters. So we'll call these theta. And if there are 4 actions, then it's going to output a vector of 4 probabilities. All right. The book uses this notation, where our policy pi, right? So the probability we take action given that we're in state S and we have the parameters theta is by definition the probability that at step t, the action we take is A, blah, 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 blah. And so in simpler terms, this is the formalism. This is in a bunch of the equations that you see in the book, but I'm just saying in simpler language that, hey, our probability is just the output of some function. So if we're playing Pac-Man, then this function has 4 probabilities it spits out, and that's all you need to know, is that in any given state, once you've trained it with parameters theta, this function is going to output 4 probabilities. Probability you want to go up, probability you want to go down, left and right, and of course they're probabilities, so they always add up to 1. You guys with me so far? All right. The toughest time that I've had is that if you look at the book, if you look at like the DeepMind, the David Silver lectures on YouTube, if you go to a bunch of web pages, this is pretty much all they say. And for me, it's very, very abstract. So what I tried to do is to say, what the heck are we talking about? What does this look like in the real world? Okay, so this is what a parameterized policy might look like in the real world. All right, you build yourself a neural network. Normally we think of the weights by layer, their matrices, whatever, but if you just listed out linearly all the weights into a giant long vector, then we would call that vector theta. Okay, you just need to remember where each weight belongs, and mathematically, yes, we still do the calculation with tensors and all that, but you could just number them from 1 to n. So in our neural network, we're going to give it some kind of inputs, like what state we're in or something like that. We can decide. You get to pick what you want the inputs to be. You give it the inputs, it goes chunk, 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 and imagine that, say this is Pac-Man. We now put a softmax activation layer on our output layer, and this is going to output 4 probabilities. And so we can say the top one is probability of up, down, left, right. And with softmax activation, then they're guaranteed to always add up to 1. So this main part of the neural network is sort of outputting these weights, and it's the softmax activation that sort of takes these weight preferences and turns them into probabilities that add up to 1. Does that make sense? Just in terms of like, instead of this theta, it's like, no, just build yourself a network that has inputs and uses softmax, and that would be a very simple way to have a quote unquote parameterized policy. So as many actions as there are that you can take, that's how many outputs you would need on your, and this can be obviously a deep neural network. Yeah, Steve?
No, I said that makes sense. Thank you.
All right. So hopefully this helps, because none of the books or papers ever have this diagram, ever have any explanation. They just simply say, your policy is parameterized on theta, and they move on.
Can I ask a question just about that last layer?
Yeah.
It doesn't necessarily have to be a softmax, correct? Like if you're doing some, I don't know, regression or something like that, saying you're doing a steering wheel and you're saying, I want to do 90 degrees left or 90 degrees right or something like that. You could just directly output that as a regression, right? It doesn't have to be probabilities necessarily.
So I think the way it's formalized in the book, okay, they're sort of saying of all of your choices, you're going to output the probability that you pick that choice. So if you had choices of 90 to the left, 90 to the right, you could have them as discrete separate outputs, and then they would be probabilities, and they would have to sum up to 1.
Okay.
But you're absolutely right. Later on in the chapter, and I am not covering it in today's slides, they do talk about the formulation of outputting just a continuous output. And so then you stop formulating it as probabilities. But as long as you formulate as probabilities, then you kind of need, it doesn't have to be softmax, but you need them to add up to 1.
Yeah.
Okay. So I'm definitely showing the simpler case where it's discrete actions.
Don't you also need it to add up to 1 just because we're talking about a policy, right? So a policy by definition means you have to choose between a finite number of actions.
Yes, you can choose one action with 100% probability, but they always have to add up to 100%. They have to add up to 1. Yes. All right. So, so if this works for you, I hope this works for you. Then this is sort of the intuition behind what the heck is this theta that we keep talking about. That I guess, you know, maybe for you guys this just makes total sense, but for me it actually took me a very long time to gain an intuition to internalize when they just simply say in one sentence, we've parameterized on a vector of weights called theta, and then they just move on. So how do policy gradients work? So now that we've sort of said what parameterizing our policy on theta means, what we do is we create a performance measure. We're going to call it J, capital J, okay? And this performance measure is what's going to tell us whether or not our policy that we're outputting, our function on theta, is a good one or a bad one. So clearly, we want our function J to have something to do with the rewards that we're going to get, because that's at the end of the day what we're trying to do is trying to maximize rewards, right? So a very simple thing we can do is we can simply say for an episodic MDP, if we start in state 0, then basically our performance measure is just going to be what is the actual value under our policy starting in state S0. Okay, so this value function is the average, the expected long-term return starting from our given state. So in this case, it's easy to define because it's episodic and everything's discrete. It turns out there are other ways you can define J, and the intuitive, the useful things that you are likely to come up with for J, all the stuff that we're talking about works. So whether you actually define it exactly this way, or if you say something slightly different, like the average reward over one time step over time, things like that. All these formulations, thankfully, the equations kind of work out the same. So if you've been doing machine learning, if you've been doing, deep learning, then you've built neural networks and you've had a scalar loss function. And the parameters, we may not think of them as a linear vector theta, but like I said, you can just take all of those weights and you can number them from 1 to n, and then just imagine that you arrange them as a column vector. Okay, so this function J is analogous to the loss function that we would use in a neural network. In this case, we're trying to maximize performance, so we're performing gradient ascent instead of descent, but it's the same process. It's the analogous process. So for supervised deep learning, your loss function gives you a signal, and what you do is you back propagate the gradients from that loss signal. So what we're going to do is we're going to back propagate the changes to our performance function J. Okay, and so just like when you're doing deep learning, this is a simplification, right? You can say my weights after an update are going to be my old weights plus some small learning rate alpha times the gradient from the gradient I'm getting from my final function. In this case, it's J instead of our loss function L. Does that make sense? We're going to go deeper down the rabbit hole. So if you're waiting, don't wait to ask a question, because it's actually going to get worse, not better. All right. So we can say intuitively, right? I've done this. I mean, even if you haven't ever worked out all the detailed math, you know that behind the scenes, that's what TensorFlow, that's what PyTorch are doing. They've got a bunch of weights. You've got your loss function, and then basically from that loss, it calculates a gradient and it does small updates. The question though, okay, so let's just pause here for a moment. We are going to get into the question of how the heck do we calculate this gradient? But before, let's just talk a little bit about why are we even trying to do all this? So there are some advantages to doing policy-based reinforcement learning, okay? Sometimes the policy space is much simpler than the value space, okay? I don't know that I have a really great example, but just imagine some, in the extreme, you have some case where it's like you have a robotic bulldozer, okay? You're in a mine and you have this robotic bulldozer. And basically, the policy ends up being, whether you're driving forward quickly or you're driving forward slowly, just keep driving forward to, with your little shovel thing in the front to pick up the rocks until you become completely stopped. And if that's the case, then maybe you need to back up a little bit or something like that, right? So you could have all this data about like the rocks and whether you're slipping on the ground or whatever, but at the end of the day, the policy is super simple. It's just keep driving forward. All right, that's a bit of a simplified extreme example, but just to give you an example where sometimes the policies are much simpler than all the details surrounding you. In general, when you're learning policies directly, it has better convergence properties. I'm not going to prove that, but that's just something for you to understand in terms of you can, well, I guess I am going to say something about that. So in a lot of the other learning that we talked about with value functions, you do this thing where you take the max when you're looking at different values. So you say, oh, I'm going to take the action that has the max. So as soon as one action leapfrogs another one in value, you have this big jump, this big change in your policy where you're switching from the old one to the new one. Whereas in this case, you're sort of more continuously, gradually switching from one to the other, which is why you tend to get these nice, smooth convergence properties. So you can see why, for example, in robotics or something like that, if you're talking about teaching a robot how to walk, right? It's nice to sort of say like, oh, okay, well, my knee bent at a certain time. Maybe I'm going to bend it a little earlier or a little bit later, as opposed to just some sort of like big catastrophic decision of, don't do a particular thing. And the policy gradients work well in high dimensional spaces. It gets really tricky when you're doing value-based and you say, what's the value of each action if you have 100 actions, 1,000 actions, or worse yet, if it's a continuous action space, it's really problematic to try and say, how do you take the max value of, the angle of the knee, if the angle could be any floating point number between, 0 degrees and 180 degrees? How can you do that? There's an infinite number of possible, angles. And if you don't know how rapidly that thing moves, it could be that, yeah, the difference between 1 degree and 2 degrees is very small. But for all you know, the difference could be huge. And that, 1.5 degrees does 10 times better than 1 degree. So unless you know that a priori, you just don't know. So typically how you would solve that in the value side is you would require someone with sort of expert knowledge to say, I can kind of chunk it into step sizes, and I know what step size is reasonable and it won't cause me problems. But you avoid the problem altogether once you do the continuous formulation of policy gradients. And then finally, you can actually learn stochastic policies. You can learn mixed policies. The stuff that we've talked about where you're taking the max value, how do you talk about 30% of the time go left, 70% of the time go right in that sort of environment? It doesn't really work. Whereas here, the formulation inherently outputs, the way I showed it, you have probabilities for all of your different actions. And if you want, you can take the max of those, but you don't have to. You can leave it as just probabilities that are mixed. There are disadvantages. So sometimes the value space is simpler than the policy space. I think that's generally true of things like board games, right? So chess, Go. I can't even imagine how you would create policies that are not based on the value of different states. Just like, I feel like moving my bishop. I don't even know how you would deal with that. Okay. One of the disadvantages of policy gradients is that they typically converge to a local optimum, not the global optimum. So we know this. We know when you train a neural network, you get a local optimum. Hopefully you want a pretty good one. But in theory, for smaller problems, the discrete value function learning methods, they will converge to the global optimum, okay? Not just a local optimum. And then the other problem is that these methods are typically very inefficient. They're sample inefficient, and I don't know if we'll really see, but what's going to come up is that they are very high variance. So it could take you, when you say that this will converge in theory in the limit if you do this in infinitely long, well, it could be that convergence time for all intents and purposes is extremely long, and that can be very problematic. If it's going to take you, a billion examples before you learn how to walk, that's going to be a problem. All right, So that's just in terms of like the background of like what it's good for, what it's not good for. So let's return now to the question of, we said we're going to do an update. We're going to do a small learning rate times the gradient of our performance measure. So let's say our performance measure is just simply the expected value following all different actions and all the possible eventualities between now and the end of the episode. What I was saying before is that's going to be the sum of a lot of these triples, which is the probability you take the action, the probability that the environment gives you a particular reward, and you wind up in a new state, and then the actual reward. So that's what we gotta calculate the gradient of. So it turns out that you first might even ask, like, well, let's see here. How do I want to? All right. So one thing that you can do just sort of as a simple process is, I don't know how many of you guys did the Andrew Ng machine learning course, but before he gets into, you know, how like TensorFlow and PyTorch really work, there's an exercise where you actually approximate the gradient. And so you take a small value epsilon, and what you do is you perturb your loss function. And what you do is, let's say you've got 10 parameters, then you perturb the first parameter by epsilon, and then you perturb the second parameter by epsilon, then the third one, the fourth one, the fifth one, and you do each of those. And if you just simply tweak your parameter by a little bit, and then divide by that epsilon, then you can calculate each of the different 10 partial derivatives. So that's one way we could do it. This is not going to be efficient. This is not going to serve us. What we really need is we need to be able to analytically say. So just like with a squared loss, you know, the derivative of x squared is 2x, you know, we know that, right? We need some equivalent of that. And so you might think that it would be very difficult to calculate this, like I said, because we've got these triple products where it's partly a function of what actions you choose, but it's partly a function of where the environment winds you up. And we're saying that we're doing model-free learning. So we don't actually know. We don't have a perfect representation of the environment's dynamics. Turns out that there's this policy gradient theorem who, you know, no surprise, Sutton is the one who proved this. He proved that there's a formula for the gradient of our function j when it's the value function, and it turns out that it doesn't actually use the dynamics of the environment at all. So we can calculate it without knowing that. If you're interested, the proof is in the book. But basically, this is what the policy gradient theorem says. It says that the gradient of this j is proportional to, here we have a sum, and this mu function is the distribution of states that we're going to wind up in when we follow the policy. We've got q, which is the value of a particular state action pair. And then this is times the gradient of our policy, function. And so this policy function is ours. We've created this, so we can take the gradient of this. And we don't necessarily know what this value is, and we don't necessarily know what this distribution of states is. But at least what you'll see here is there's no, in the book, what we're using is this function p. There's no function p that says what's the probability that the environment dumps you in a particular state, or that the environment gives you a particular reward. So in this formulation, basically, we had that term, and he shows that there's a way where you can get all those terms to cancel out, so that you're only wound up with things that are kind of under our control. All right, so I clearly did not prove why this is true, but do you guys have any questions just in terms of like this particular formulation here, in terms of what we're going to do with the policy gradient?
Can you go back to, I think it was last slide.
This one or the one before?
I think, yeah, it's that one. So that first bullet point, I think mentally, just thinking about policy gradient, for me, my sort of simplified view of it is we're just trying to directly pass signal to the policy, and we're skipping a lot of the other steps. But part of the complication, from my understanding of that first bullet point, is that changing your policy changes what you're viewing. So you might end up with a policy that only does one specific thing, and then it kind of just nukes everything because you don't actually do proper exploration. Is that kind of what that first point is saying?
There is an exploration problem, but it's even more intrinsic than that. It's saying that let's say you're playing an Atari game, okay, and like let's say you're playing Pac-Man. When you get one of those power-ups, like the game's like completely different. You know what I mean? Now you're chasing the ghosts instead of the ghosts chasing you. Okay. If you're trying to, get more points, right? So, so the thing is, if you're right next to a power-up, choosing to go eat the power-up or choosing to go the other way wind you up in very different states. So not only are you changing, when you tweak the policy, not only are you changing the actions you take, but then you're also changing the states you wind up in. And so then the subsequent actions and everything can be very different from depending on the two choices, right? So the value of doing these things can kind of really diverge, right? So like, I hope everyone here knows Pac-Man, because I'm going to keep going with this analogy. So like you could imagine
That's a really helpful analogy. Thank you.
You can imagine you've cleared the board and all you have left is one power up and one food, whatever, pellet. I don't know what they're appropriately called, right? Like you can imagine in that scenario, if you ate the power pellet, at that point, what you want to do is you want to chase as many ghosts as you can and get some points before you turn around and go back and eat the last pellet and finish the level. If you just take the power up and you immediately eat the pellet next to it, you will then finish the level. You will have no opportunity to chase ghosts anymore, right? So normally eating a pellet is a good thing, but in this one scenario, because it's going to finish the level, when you have a power up, you'd like to get a couple extra points by catching some ghosts. I don't know, but so that's an example where the action you take leads you to very extreme different environments. And so is it really clear that you can even predict this? Because remember, we've got no value functions. So we don't really know that technically we don't know that chasing ghosts is good, right? We just have this function that outputs left, right, up, and down. It's got no notion of value per se. It's just spitting out left, right, up, down.
And so part of what you're saying is if we had some sort of value estimation, the value estimation might tell us, okay, I get a certain amount from picking up this power pellet, and then I get a small amount from picking the final pellet, but I get even more points from eating a ghost.
Right. But
And
we're doing policy learning, and there is no such thing as a value function that tells you you get 100 points for eating the ghost.
Mhm. Yeah.
So you might imagine it might be very difficult. It might be very difficult or very slow or require some luck for the policy to eventually learn that.
Mm-hmm. So in the other approaches, it's explicitly calculating that, so it has something that is directly trying to tell it this is the more valuable move. But in the policy, it doesn't have that. So you can
That's
hope
right.
that it learns it, but it isn't as implicit.
You know, in value-based learning, you still could imagine it might take you 1,000 games of Pac-Man, but you're going to kind of figure out, oh, eating a power pellet's good, and eating a ghost after a power pellet is really good.
Mm-hmm.
And then, you know, over many, many, many more games, you then learn to balance. But if I use up all the power pellets right away, then I might die and never finish the level because I'll never, you know, clear the board, right? So I you know, I don't just completely exclusively go after ghosts. Maybe what I want to do is I want to, you know,
Mm-hmm.
when the ghosts get faster, then at some point I have to just sacrifice chasing ghosts and just try and finish the level. Okay. But in this case, we have none of those things. You know, we know what all the states are, so technically we know the difference between we ate a power pellet, we didn't eat a power pellet, but we have no value functions. We're just simply saying we have this. So the inputs tell us that we're in a different state. We're in a state where we've eaten a power pellet and the ghosts are flashing. But that's all we have. There's no values. And all we're going to get is left, right, up, down as an output. Okay. So it might be pretty tricky. So that's what I'm saying here in this first bullet. So the cool thing is with this policy gradient theorem, it says that you actually don't need to know the dynamics. And to give a little bit of intuition around this, so the gradient, right? That's just like the slope. It's a multidimensional thing, right? But it's the slope of fastest change. It's the direction of fastest change. And in this case, J is, we're saying it is our value function. So we're not storing values like value-based learning, but J ultimately is what we're trying to do is to figure out, you know, the gradient on our value. And so if you look at the right-hand side here, it's saying the states, because this mu function is the states that you wind up in when you're following the policy. So obviously the states that you wind up in more are going to matter more than the states you wind up in less. So that makes sense that you're going to multiply, you're basically weighting this right-hand side by whichever states you wind up in most. And what is the right-hand side? Well, the right-hand side is basically saying it's the value that you get for taking a particular action times this gradient of the actions that you choose. And so it makes sense also that if you have 4 actions and one of them's worth 100 and the other 3 are worth 0, that you're going to multiply 100 by, you know, moving in that direction. So it sort of makes sense, this overall equation, that it's saying that the gradient, the direction that increases our value the most, is heavily leaning on whichever states you're in the most, which extra actions are worth the most times that direction. I hope that gives just like a little bit of intuition. So it turns out that this formula can be reformulated. Okay, not going to show the proof. Sutton doesn't exactly explicitly show this proof, but he does mention, there's sort of part of it he mentions in one place and another part he mentions in another place. But basically, when you have the gradient of this function pi divided by the same function pi. So when you have the gradient of something divided by itself, if you know from calculus, the derivative of 1 over x is ln x. And so that's how you actually wind up with this log in here. And so we can reformulate it. It can be shown that the gradient of our performance function j is the expected value, that's what this e is, the expected value of the long-term value from a given state in action times the gradient of just the log of the function instead of the function itself. And so once again, this makes sense that the more something is worth, that's going to push the gradient in that direction. The less something is worth, the less it's going to push it in that direction. That's the general gist of it. So like I said, I really struggled with some of the math because in the earlier part with value functions, the math was all sort of about adding up returns, adding up rewards, and I could deal with sums, but now we're not just dealing with sums, now we're dealing with derivatives, and it gets the maths even a little bit hairier. But if you can either, if this either makes sense, or if you can just sort of like take it on faith that this is what it is, then we can actually form a policy learning algorithm just using that formula. And so the simplest way we can do this is we're going to do a Monte Carlo technique here. So again, this is not necessarily the approach that people use, but this is the simplest way to talk about it. So we use this as a starting point. So if you're doing a Monte Carlo method, what that means is you're going to start in a certain state and you're going to run things out according to your policy until you get to the end of the episode. And if you do that, then sort of the sum of all the rewards from now until the end of the episode, that's what we call G, okay? So if we start in state S at time t, then G sub t is the return that we get. So going back to the previous equation, this function Q is the long-term return for a given state and an action. And how do we estimate what is the long-term return of this? Well, one way we can do it is the Monte Carlo way, where you take lots and lots of samples, where you start in this state and you take that action, and then you just average out what are all those different returns over time. All right. So if we could average out a whole bunch of returns over time in order to approximate this estimated value, another way of saying it is we just simply substitute the return for that Q function here. And so we're saying, oh yeah, our performance gradient is going to be the return times the gradient of this log. So if that is what your gradient is, what is your update? Well, your update is simply going to be alpha times whatever your gradient is. That's what you do in gradient ascent or gradient descent, right? In gradient ascent, you add alpha times that. In descent, you subtract alpha times that. So we've got our parameters, and remember, this is just a neural network with a bunch of weights, and we're saying the weights for the next time step is the old weights plus alpha times, in this case, the return we actually got, playing out this game to the end, playing out to the end of the episode, times the gradient of the log of our policy function. So here's the algorithm from the book, and what you will see, the key part here is that you have to generate a full episode. So you start in your state 0 and you keep going until you get to the end of the episode. And we're going to calculate our return. In this case, it's showing the discounted case, so it's got discount factor gamma here. But the return is just the sum of all of the rewards. And so each time you go further down, you discount. So gamma, you can do gamma and then gamma squared, gamma cubed, so on and so forth. But so this is just the return as we're used to it. And it says we're going to update our weights based on alpha times, we've got this, again, this discount factor gamma here, but basically alpha times our return times the gradient of the log of our policy function. So if you're implementing this in PyTorch or TensorFlow, okay, it has an autograd, it has an automatic gradient calculating thing here, right? So if we put in, alpha times gamma times the actual return times the log of our policy function, then TensorFlow or PyTorch will automatically calculate the gradient, and then you can just tell it to do an update. So like in PyTorch, it would just be what is it? It's a step, I believe, the name of the function. So you just tell it to take one step. Just as a tiny note, because TensorFlow and PyTorch are hardwired to do gradient descent, and we're trying to do ascent here, you actually have to multiply this by -1 because it thinks it's doing gradient descent, and so you just change the sign on everything. And so I saw that in, I think it was David Silver's video. He says, by the way, if you program this and it totally doesn't work, it might be because you got the sign wrong and it's still trying to do gradient descent and you want it to do gradient ascent.
Hey, Ted, quick question. So can you remind me really quickly, if we are calculating G for, let's say, a game of chess, G is just like 0 or 1. I won or I lost. Is that?
Yeah, so you play until the game ends, and you do actually 1 or -1, I think is usually how they do it, right?
Okay. So,
and so you've got a 1 or a -1, and then if you're in chess, I don't think you really need to discount it. Okay. And so you've got a 1 or a -1. And so basically you are going to do alpha times 1. And so if this is undiscounted, it's just 1. So then basically you're just going to say, I'm going to bump my weights in my neural network by this small learning rate alpha times 1 if I won, right? Times the gradient, all right? And if I lost, then I'm going to move in the opposite direction. I'm going to do -1 times the gradient.
got it. Thank you.
Right? So at my given moment, if it was move my queen here and let it get captured, then it's going to say, okay, tweak the parameters in a way that reduces the probability that you're going to move your queen there and get captured because you did this 1,000 times and you lost the game 999 times.
Yeah, exactly. Okay.
Okay. So the transition from sort of this previous screen, this formula which says expected value, to an algorithm is now we're saying if you do this update thousands, millions, billions of times, then these returns will actually average to your expected value. And so that's how you get from, you're never directly calculating the expected value, right? But you're approximating it by saying, I'm going to do thousands, millions, billions of these and average them. And then in this real world situation, you would pick different starting states and you'd be sort of in parallel updating all of these different things. And so, you can be learning about lots of different things at once, not just learning one particular state, one particular move. All right, you guys with me? At least enough with me to keep going? All right, so here's our simple case. Again, it's kind of easier to think about a Monte Carlo situation where you just, like Steve said, you play out the chess game and you see whether you won or lost, 1 or -1, and then you use that as feedback to tweak the weights in your network. So when we were studying value-based learning, we started with Monte Carlo because it's sort of easier. But then eventually we transitioned to other techniques where we don't have to wait until the entire game ends. There's two problems with waiting until the game ends. One is it's very sample inefficient, okay? But the other problem is you have a credit assignment problem, all right? So 80 moves transpired, and how do you know that this move of my queen is the one that really was bad versus one of the 78 moves that happened before I lost the game? All right. Now it's true that with infinite time, this will average out to telling you whether or not it's a bad move, but it could be very inefficient because you've got these 78 other moves that, you know, are also tweaking things. So what we showed, oh shoot, I forgot there's another slide in here. Hold that thought for a moment, because we're about to do the transition from Monte Carlo to basically one step, just like we did when we switched from Monte Carlo to temporal difference learning. But so this is, we started by showing sort of the simplest possible way that you can do policy gradient control. The thing to know is that, again, what I was trying to say less formally, now I'm going to say it formally, are that the average returns G over time are an unbiased estimate of our value function Q. Okay, so in other words, if you did this infinitely, many, this will be an accurate estimate. You can get this as close as you want to the accurate value of Q just by doing a lot of them and averaging them. The thing to know, however, is that this estimate is high variance. And this is a fundamental problem that causes a lot of grief with policy gradient learning. An example I saw is that let's say you're building a robot to navigate some world, and it has a bad policy, and it just goes into a corner and just like drives right into the corner. All right. The problem you have is that in this case, the feedback you're getting is intricately correlated with the actions you take. And so if you take a really dumb action, like just driving into a corner, there's the feedback you get is all related to being stuck in a corner, and it's not actually telling you much about what would happen if you had gone down the hallway instead of, driving yourself straight into a corner. And so it's hard to get out of that situation because you're doing something bad, and the feedback is just it's so skewed by sort of this situation that you're in. So hopefully that helps with a little bit of intuition. So in the book, they show the proof. I'm not going to show it here, but it can be shown that your reinforced algorithm that we just saw, the estimate remains unbiased if you subtract a baseline from it. So here in this algorithm, we're using G. We're using our actual returns. We don't have to use G. We can subtract something from G. It doesn't have to be a constant per se, but it does have to be constant for a given state. It can't depend on the action. So this baseline B can be a function of what state you're in, but it can't be a function of the actions you choose. If it's just merely a function of the state you're in, then this update was alpha times G times this gradient. And now it becomes alpha times G minus a baseline. If you do this, then the size of these quantities is a little bit smaller, and you get the same estimate, but it actually reduces the variance sum. And so the question is, what would you want to use for your baseline for a given state? Well, actually, the perfect choice for this would be if we knew what the value function V for that state is, we could subtract that. And so then basically this would be zero based. If you did an average action, then G minus V is going to be 0. If you did a better action, it's going to be positive. And if you did a worse action, it's going to be negative. And so one thing you can do is you can use instead of doing a pure policy grading thing, now we can, in parallel, do the old technique. We can do Monte Carlo and we can estimate values, and we can do the policy grading thing. And then where we combine them is, instead of doing the update rule with just G, we do G minus our current estimate of what the value of that state is. So this is our first foray into saying, let's not be such a Puritan about saying we're going to do policy-based learning only. We can actually try to have the best of both worlds. We can do value-based learning and we can do policy-based learning. And so that leads us to, really nobody does just pure policy-based learning, okay? So that leads us to actor-critic methods. And where this name comes from is your policy learner, that's your actor. And your critic is your value-based function giving some kind of feedback, some kind of criticism, some kind of guidance to your so-called actor, okay? It's giving extra information. And this little Venn diagram shows that theoretically the reinforced algorithm was straight policy gradient. We talked a lot about Monte Carlo, temporal difference, SARSA as value-based. So actor-critic methods are where we're going to use both. And a simple way we can do this is, we said in the reinforce one, we're using full episodic returns G. And how you estimate that is you do a full Monte Carlo episode. So where I was trying to lead to, I forgot I had a couple more slides in here, is that rather than waiting to the end of the episode, we can just go one step and try and do an update. This is exactly what we did with value-based learning when we went from Monte Carlo to temporal difference. So here is a one-step actor-critic. And if I can just turn on, here we go. So you sort of initialize everything, blah, 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 blah. Then what you will see is you're going to take an action and you're going to wind up in a new state and you're going to get a reward. In the reinforced algorithm we saw, we then immediately try to do an update to our policy. Instead, what we're going to do is we're going to calculate this delta, which is the reward plus the next state's value minus our current estimate of the value. This is the exact same formula that we used in temporal difference learning, okay? There's no change here. This is just temporal difference learning. So we're going to say, we're going to calculate this delta, the temporal difference, and we're going to do a learning step for temporal difference learning. Just so you know, the reason why this formula looks different is because now, instead of everything we talked about earlier was tabular based, where we just got a full table listing every state. Now this is actually approximating that value function with its own neural network that has its weights W. Okay, so we skipped 4 chapters in the book that talk about how to do approximation and stuff. So this looks a little bit different, but what they're really saying here is just do temporal difference learning, okay, to get your value function V. Then the only change in this formula down here, here's our theta, the theta, that's the same, alpha's the same. The terminology is a little bit different than what I have on some of the slides. This gradient is the same, okay? The difference is that we have substituted our delta, our temporal difference learning step, from G, our full return. Okay. So this is the big difference right here, this delta. We used to have a G here, now we have got delta. Does that make sense in terms of we can immediately do an update after one step instead of waiting, 80 moves to the end of the chess game to do an update? Yeah? All right. If you are really sharp, one thing you will see is that, but wait a second, this is only a one-step update. This this might not capture everything, all the downstream implications of what I did here. Okay, and that is accurate. So when you do a one-step update, you no longer have an unbiased estimate. This is a biased estimate. It is not guaranteed that even if you did this a billion, billion, trillion, billion times, that you would converge to exactly the correct value here. The difference, however, just like with Monte Carlo and temporal difference in the value learning scenario, is that this estimate, while biased, is much, much lower variance. And in practice, just like TD works better than Monte Carlo, in practice, this one-step actor-critic works better than reinforce full Monte Carlo policy gradients. Now, there's this whole part of the book and reinforcement learning that we haven't discussed, which is basically there are actually shades of gray in between. So last session at the very end, I showed sort of a square, and in the corner you have one step, and in another corner you have full Monte Carlo. And actually you can do in between. So instead of doing one step, we could actually do two steps. We could do three steps. And there's even a formulation that they use in reinforcement learning where you do kind of a weighted average of one step and two step and three step up to some number. Okay, so there is a lot of middle ground between the idea of full Monte Carlo and just a single step. But all of these shorter updates are more sample efficient, they're more frequent, they are slightly biased, less biased the more steps you go out. So if you go out 5 steps, it's a lot less biased than just one step. And the big thing though is they're much lower variance than the full Monte Carlo. So that's a very simple actor-critic where, again, we're doing the policy gradient update, but we're also in parallel calculating the value function for each state. There are things that we're getting to the end here. So there are things that people have done to say, how do we make these better? The math on some of them would take me a really long time to figure out. But if you look at like stable baselines, they've got this is most of the algorithms that they've implemented in stable baselines 3. I think there's one extra one here. And so what are some of the things that they do differently? So there's A3C and A2C, and what they do is they do kind of a baseline-y thing where the advantage is basically the reward minus the average reward. Okay, so they do a baseline-y thing, but then they also, instead of just having one learner, they've got multiple learners, multiple actors going in parallel. So A2C is advantage actor-critic, and A3C is there's an asynchronous version of this. So there's A2C and A3C. So asynchronous does this weird thing where the actors are all updating separately, whereas this version, they all take steps and they all do one big update together. You need to tweak the way you're doing things if you want deterministic policies. If you don't want a mixed policy with 70% left, 30% right, if you just want a deterministic policy, you have to fiddle with some things, because if you just take a max and super simplistically try to make it deterministic, then what'll happen is it won't explore. And if it doesn't explore, then it won't learn. So, so DDPG is a way to do deterministic policies, but also still explore. Another way that they sort of address the high variance problem is trust region policy optimization, TRPO. They figured out that if you don't allow the updates to get too big, if you clip them, if they exceed a certain size, then that helps reduce the variance. The question is, what is the size? What do you say is your clipping boundary? And they do some heavy duty math, and there's this complex calculation that says if you do this, then it has nice guarantees. but it turns out that that math's really expensive. So in fact, stable baselines doesn't implement TRPO, that implements PPO. PPO is a pretty famous algorithm. Okay, you're going to see it a lot. So proximal policy optimization does an approximation of TRPO. And so it's a much faster, simpler calculation, and it's easier to implement, and it's good enough. So people do PPO instead of TRPO. You also hear about soft actor-critic, SAC. I don't know if I completely understand this one, but basically, when we talk about things like epsilon soft policies before, we're saying that instead of always doing the thing that you think is best, sometimes you're going to do something else. You're going to explore a little bit, okay? And so there's I don't know all the details, but there's a similar idea here where they use the entropy of the policy in order to calculate sort of like a penalty term to the reward. And so then basically what this says is that if you know, like, I don't know the exact formulation, but it's sort of like if you've been doing the same thing over and over again for a super long time and you haven't tried something else, then you're going to sort of get penalized, and eventually it's going to flip it to encourage to try one of the other actions. So PPO, soft actor-critic, very famous algorithms. And then there's another one here, twin delay, deep deterministic. So I think I might have mentioned double DQN at some point, but the whole idea is if you have two different networks, then you can solve sort of some problems where, again, you have correlation between your policy that you're choosing things, how that's being estimated, and the value function that you're using. And so if you sort of like take the policy from one and the value from the other, then you kind of do a better job, you have less variance. And so they use those same tricks. And so then they take and they apply those to DDPG. So, all right. I'm just in time for our ending time. I don't know if I got everything 100% right, but what I'm hoping is that this covers enough intuition around why might you want policy gradients. Okay, smoother learning, definitely continuous action. So if you're doing robotics and you have like continuous motion, we didn't talk about the continuous formulation, but all the formulas we showed can be tweaked for continuous actions. And then ultimately, you can kind of have the best of both worlds, where you calculate a value function and you use that to help the way that you're learning. You can do what we showed, the one-step actor-critic, and then there's these other further optimizations, largely to reduce variance and try to get this thing to learn faster, and also to try to not have it get stuck like a robot that just goes into a corner and cannot figure out what to do differently. It just keeps, banging its head on the corner. All right, so that was policy gradients in what feels to me like a very fast session. So any comments, questions?
That's a really great overview. Thank you, Ted.
Yeah, I'll second that and just say really good job, Ted. Thanks for putting all of the effort across all of these weeks.
Yeah, thank you very much. This has been really interesting.
Yeah. So be honest with me. Did some of this make sense, or did it all just kind of go whoosh?
Well, the parts that went whoosh, I think, was my problem, not yours, and but a lot of it did actually make sense, and so yeah.
Ted, you asked that question very appropriately. So the true answer is some of it made sense.
Okay. All right. Well, I'm glad at least, for everybody, at least some of it did, because like I said, I really struggled with this. There's a lot more math, and then the Sutton Barto book's a little bit older, And the chapter on this is actually really short. It's like a dozen pages. And so it's just like a whole bunch of math. There's not a single like real worldy example of Pac-Man. There's no neural networks shown. It's just sort of like a whole bunch of Greek letters. So if you don't get everything, hopefully at least some of it. And so then if you decide to read some of these reinforcement learning papers, or if you decide to read chapter 13, that'll help ground you in terms of what's really going on here.
It
All right.
was a very good overview. I would like to know more about mathematics, though, but I understand that, well, I'm a minority here on this, and I shouldn't push my, opinion.
Well, you definitely can start with chapter 13, and then I would say like the DeepMind videos. There's one on policy gradient algorithms, and then also this website. I'll post the slides to our GitHub, but she does a good job going over some of the math, and then she has many more algorithms than this where she explains it in more detail.
Mm-hmm.
So you can definitely have
Thank
fun
you.
with that. Yeah.
I-
All right.
I think for me, the math is important and the theory and all of that stuff, but I think the thing that I didn't necessarily get out of this is I've got some problem that I think is a fit for reinforcement learning. We've got all of these options, and I have some intuition of, oh, maybe this one might be a little bit better for this or a little better for that. But I still feel like I'm a little bit weak in that regard. Like on that slide, you have all of the different options. Which one probably fits best for my problem and why? Like, do I just try them, or is there some experience that you can get over time from trying these things and understanding which ones seem to be the best? Because it doesn't seem like one is just categorically like, just use PPO every time and it'll turn out good.
Well, in terms of choosing between these, I don't know. Maybe there's sort of one that's sort of like the latest that people lean towards. But what I would say is, like, if you go to stable baselines and you look, they have like just the simple one that's, I forget what it's called, pole cart. It's just a vertical pole, and you can move left, right, and you're trying to prevent it from tipping over. Okay, so that's an example where the policy space is a little bit simpler than the value space. They're actually both pretty simple, right? But in the case of the value space, if you're sort of thinking about where you are and how far the pole is tilted, there's a lot of different combinations of those things, right? Whereas in the policy space, kind of what you most care about just is how much is the pole tilted. You don't really care as much about everything else. And so you're just basically saying, if it's tilted to the left, move to the left. And that's a pretty simple policy. I mean, there's some like fine tuning on it. But basically, you could do a very simple policy that simply says, if the pole's tilting to the left, move to the left. If it's tilting to the right, move to the right. Done. That's my policy, right? Whereas in the value space, you just have many, many more states, that you're keeping track of. I think anytime you see, I forget what they call that whole section, Ryan, the one that has the cart pole and the cart hill and all those. I think you're going to find that the value-based ones don't really work on those problems. I think it'll work on the cart pole because it's so simple, but for all the other ones, it doesn't, because basically it explores and it never, ever, ever accidentally stumbles upon a solution.
Mm.
You're supposed to like push the cart, all the way back, and then it let gravity take it all the way up, and then you have to do it like multiple times before it gets to the top of the hill. Like, you just never ever successfully randomly choose up, and then down, 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 down. You know what I mean? Enough times in a row if it takes like, I don't know, 50 different actions. But if you have a policy that says, oh, when you're moving left, push left, when you're moving right, push right, then that simple policy will simply then get the cart to go, back and forth until it gets to the top of the hill. So I would say that, like, whenever you have those kinds of dynamics, that's where likely you can do some combination of policy gradients plus one of the things I don't think I said is that you can insert expertise into how you formulate that parameterization of the policy. So when I showed, actually it's quite a few slides, but when I showed this neural network, right, you can insert expertise into what these inputs are. And so, you can say, oh, what's the velocity of the cart? Oh, what's the angle of this? What's the, you know what I mean?
Mhm.
And it's a little bit, I don't know, less clear how you do that in a value-based world to try and, inject. But you can easily see that if you had, let's say, sort of an expert notion of what you think the policy might be, you could just sort of start with that as your baseline inputs and then allow it to do various tweaks and then ultimately output, what it wants to do. So what I would say the opposite of that is, so in 2 weeks, you're going to talk about AlphaGo, right?
Mhm.
Something that I think something like a board game has very clear connections between the board position, the state, as it were, and the value. There's a very direct connection between what pieces you have left on a chessboard and the value of that position. Where those pieces are is subtler, but that's also important, right? And in Go, it's the same thing. If you're kind of surrounding your opponent, whatever kind of thing, then that's highly valuable. Go's trickier because if you've got a big board, you've got all these dynamics, are you surrounding them or are they surrounding you? It's sort of hard to say, but that's the gist of it. So anyway, that's my sort of high level 2 cents in terms of choosing between value based and sort of policy based. So I think robotics and whatnot, you're going to see it's all policy based. But poker, Atari, StarCraft, I think you very much want to lean more on the value side.
Yeah, and we'll discuss more in a couple of weeks, but lots of stuff going on there.
Yeah. Cool. Anything else? I know we're over time. I didn't hear any dings. Oh, so we may have a few people joining us for the project session, but we always say it's approximate, so they can put up with just the tail end of the
Hey,
book club.
Ted, what was it you were going to post in chat? A link to something.
Oh, I'm going to put these slides up. I don't think I have even put the last 1 or 2 sessions, the slides up yet, and the videos. But if you want this link here,
Yes.
you could do a screenshot right now, and then you don't have to worry if it takes me several days.
It is just, it would be easier to click in
Oh,
the
actually,
chat,
here.
please.
Wait. Here we go. Hold on. Oh.
I'll end the recording here.
Okay.